The Fukushima nuclear fallout. On March 11, 2011, after an earthquake and a tsunami that devastated the northeast coast of Japan, a multiple core meltdown happened at the Fukushima Daiichi nuclear power plant, leading to a substantial release of radioactive material into the environment. Due to a general lack of detailed radiation measurement, Safecast, a citizen science group based in Japan, started building instruments for geolocalized measurements of radioactivity. The idea of the project was to reconstruct a map of radioactivity from these measurements. Let us first consider the following simpler one-dimensional problem. Suppose that you are interested in a continuous time function, f of t, that is only known through some discrete set of measurements, the known samples here on the right side. In addition, these measurements might not be uniformly sampled, that is, they do not lie on a regular grid. We would like, nonetheless, to be able to say something about the value of the function in areas where no data is available. If it is possible to make a few assumptions about the function itself, it is then possible to make an educated guess about the value of the function at locations where the signal is unknown. This process is referred to as interpolation. In our example, we will consider the particular case of band-limited functions. We can see here a band-limited interpolation from the known samples. As you can see, the dotted line, or the continuous time function, goes through all the red samples, so it does a perfect match at the known values, and it interpolates in between. Let us consider a continuous time t-periodic and band-limited function f of t. Since it is band-limited, this function can be parametrized by its Fourier expansion coefficients up to a finite order m. This means there are two m plus 1 Fourier coefficients that are conveniently represented in vector form by a vector c. So here we have the expression of the periodic function, which is the expression of a Fourier series that we study in this class, and the vector is given here by two m plus 1 coefficients. We assume now that we know capital N pairs, ti, zi, where zi is the value of the function at time ti. We do not make any assumption about the locations of the ti's. Given n large enough with respect to the maximum Fourier coefficient order m, we can make a least squares fit of the data to find the Fourier expansion coefficient that best approximates the data collected. We need at least n equal 2m plus 1 measurements, but in general we would like a much larger number because of possible measurement noise. The least square fit can be rewritten in matrix form and solved efficiently, but let us skip the details here. For a full demonstration, see the corresponding IPython notebook. Once we have recovered the best guess of the Fourier expansion coefficients, it is possible to resample the function f of t at any location we like. Often, the function is resampled on a regular grid. Let us give a first example. The function we chose here satisfies perfectly the assumptions of periodicity and band-limitedness. It is just the sum of two sines of frequency 1 Hz and 4 Hz. The true function is represented by the thick black line. We pick at random 20 samples represented here by red dots. The model order is m is equal to 6. The interpolation given by our least squares fit is the dotted red line. Since all the assumptions are satisfied, and because there is no noise, the interpolation recovers perfectly the original signal. You might be wondering what happens if the original signal does not satisfy some of the assumptions, as we might very well be the case in practice. For example, assume the signal is not band-limited. We take here the example of signal continuous everywhere, but not differentiable at zero. Such a signal is not band-limited. However, its Fourier coefficients decay proportionally to the square of the frequency. That is quite fast. The non-band-limitedness of the function can be somewhat compensated by picking a larger order for our model and having more samples. We choose here the order model to be m is equal to 10 and take n is equal to 20 samples, picked again at random. We can observe that our interpolation is still very close to the true function, The approximation is, however, not so tight around the sharp angle at t is equal to 0. Let us now move on to the real-world example of Fukushima. We are interested in measuring radiation levels all over Japan and beyond after the tsunami of 2011 and the nuclear accident. Instruments were loaned to volunteers in the field, and measurements were carried out by fixing the sensors on cars. The sensor would then take a measurement of the radiation every 5 seconds. Therefore, sampling is generally limited to areas accessible by car. A subset of the measurements is shown here on a map of the Fukushima prefecture area. Each colored dot is a measurement, with yellow being low intensity and red high intensity. You can observe some fairly high measurement levels on the path of the plume, starting around the plant situated at the far right of the map and going northeast. This is a typical example where the location of measurements is constrained by available infrastructure. Since the measurements are done with a car, we can only measure on roads, as plainly visible on the map. It is thus necessary to apply interpolation to get an estimate of the intensity of radiation in areas where no samples are available, such as forests, fields, and so on. The interpolation is done using a model with m is equal to 441 Fourier coefficients and a number of samples that is close to 1,000,000. The function so obtained is then resampled on a regular grid and displayed here on the same map as before. A decent estimate of the total radiation field is obtained in this way. A few caveats are to mention. First, radiation is notoriously non-band limited, and we would probably need a larger order model for better approximation. Second, large measurement noise is present and also degrades the quality of the estimation. A few tricks were used in this reconstruction to improve the quality of the estimation. The code and detailed explanations are available in the companion IPython notebook. Check it out.